In this video here, we're going to take a look at exam revision for radians. So for this video then, all we're going to do here is run through a few different exam style questions based on radians. And as you can see then, this will cover the following topics here. So we have an introduction to radians, we then look at arc length, we then have areas of sectors and segments, we then want to look at how we can solve trig equations involving radians, and then finally here to finish with, we have the small angle approximations. So as always then, what I'd recommend here is that you pause the video and have a look at the questions as they appear, and then just double check that your solution matches what we get on the screen. So that should give us everything that we need here to get started. Let's begin now with question 1. So let's just get started here then with question 1. So for this question here, we're given that theta is small and measured in radians, so we want to use the small angle approximation to show that 4 cos squared theta minus 2 sine theta is approximately a plus b theta plus c theta squared, where a, b, and c are integers to be found. And what I've also included here then is the small angle approximations as they're given in your formula book. Okay? And of course, we can just use these where necessary. So to begin with here then, looking at the left-hand side here then, that's this expression. I can see that we have sine theta. Let's just highlight that here then. So sine theta. And we also have cos theta. Now, the cos theta is square, but that doesn't matter too much. We'll just square that when necessary. So we also use cos theta here. There's no tan theta, so we'll just cross that off. We don't need to use that. Okay? So basically, all we need to do here then is replace any sine thetas with theta and replace any cos thetas with 1 minus theta squared over 2. So in that case, then what I've got here is 4 cos squared theta. So what I've got then is 4 times by cos theta, which is 1 minus theta squared over 2. So 1 minus theta squared over 2. Now we need to square this, right, because it's cos squared theta. So we square that like so. And now we subtract 2 lots of sine theta. Now sine theta is approximately theta. So altogether then, we have minus 2 theta. Like so there. Okay. So what we now need to do here is expand these double brackets. And that should be pretty straightforward, right? We are doing A-level maths. So expanding these double brackets here, what do we get then? So we get 4 lots of the following. So I get 1 minus theta squared plus theta to the 4 over 4. So theta to the 4 over 4. And again, don't forget the minus 2 theta here. So minus 2 theta there. Okay. So now if we expand here with the 4 on the outside, I get 4 times 1, so that's 4. 4 times minus theta squared gives us minus 4 theta squared. And then 4 times by theta to the 4 over 4. Well, the 4s would just cancel and we just get theta to the 4 there. Okay. And again, don't forget the minus 2 theta here on the outside. Like so. Now, you might be confused here because the result that we want to obtain here, so that's a plus b theta plus c theta squared, doesn't involve any thetas to the 4 here. And the reason for that is because we can ignore the theta to the 4 term. Let's just make a note here. So ignore the theta to the 4 term. The reason that we can do this is because theta is small. Okay, so given that theta is small here, we can just ignore theta to the 4. Okay, so ignore the theta to the 4 term as theta is small. Okay, so in that case, then what we get left with here is 4 minus 2 theta minus 4 theta squared. And just notice then that at this point here, we now have it in this form. Okay. So in that case then, a is equal to 4. So a is equal to 4. B is equal to minus 2. So b is minus 2. And then finally here, c is equal to minus 4. Okay. And there we have it then. So that gives us the solution there to question 1. So moving on to question 2 here then, as we can see, right, we want to solve this trigonometric equation here. So we're solving for x between 0 and 3 pi, given our answers in radians then, this trigonometric equation here, and we need to show all of our working clearly. So for this question here then, let me just begin by writing down this trigonometric equation. So we have 7 cos x. So 7 cos x minus 2 is equal to 2 sine squared x. So 2 sine squared x there. Okay. Now for this trigonometric equation here, you need to recognize that we do need to use a trigonometric identity. Okay. So just recall them. Let's make a note here. That's sine squared x plus cos squared x is identical to 1. Okay. And what we can do here now is rearrange this trigonometric identity here in terms of sine squared x, and we can substitute that into this equation here. Okay. So sine squared x then. So sine squared x is equal to 1 minus cos squared x. So 1 minus cos squared x there. And as we've just mentioned, right, all we need to do now is just substitute this into this trigonometric equation here. So if we do that here, then what do we obtain? So the left-hand side won't change, right? That's just 7 cos x minus 2. So 7 cos x minus 2 there. So what I've now got here on the right-hand side is 2 lots of this here. So we get 2 lots of 1. So 2 lots of 1 minus cos squared x. Like so. So if we expand this out here then on the right-hand side, obviously the left-hand side again won't change. We get 7 cos x minus 2 is equal to 2 times 1, which is 2. 2 times minus cos squared x there gives us minus 2 cos squared x. Okay. So what I'm going to obtain here then is a quadratic equation. Okay, and obviously the hope then would be that we can factorize that quadratic equation. So let's make the quadratic term here positive. So add that to both sides then. So we get 2 cos squared x. So 2 cos squared x. I've got 7 cos x as well, so plus 7 cos x. And given that we want to obviously solve this quadratic equation that we're about to form here, it would make sense to make one side of the equation 0, right? So let's also just subtract 2 off both sides. So minus 2 minus another 2 gives us minus 4 there. Okay, and this here then is all equal to 0. So at this point here then, as we already mentioned, right, we want to hopefully solve this by factorizing. And the good news here then is that we can indeed factorize. So what we obtain then is 2 cos x. So 2 cos x minus 1 in my first bracket. And then in the second bracket here, we're going to get cos x plus 4. So cos x plus 4 there. And this here then is all equal to 0. So from here then, what we can see is each term here, or each factor would be equal to 0. So 2 cos x minus 1 is equal to 0. So just solve for cos x here. And in that case then, nice and straightforward here. We obtain that cos x is equal to 1/2. So 1/2 there. And then with this factor here, we obtain that cos x is equal to minus 4. So cos x is equal to minus 4. Now hopefully you recognize straight away then that this trigonometric equation here has no solutions. So no solutions here. Let's just make a note of that. So no solutions. I'll just cross it off here just so it doesn't cause confusion. Now for this trigonometric equation here, this does indeed have solutions, right? So what I'm going to do here is use a cast diagram. So to begin with then, let's just take cos inverse of both sides. So x then is equal to cos inverse of 1/2. Now just ensure then that your calculator here is in radians mode as opposed to degrees, right? Because we need to give the answers here in radians. So if you do this correctly here, then what you should find, or what your calculator should give you here, is pi over 3. So we obtain pi over 3 there. Now to obtain the remaining solutions here, what I'm going to do is use a cast diagram If you don't like the cast diagram method, that's absolutely fine. You can use, say, a graphical method. Again, that's absolutely fine. I personally prefer a cast diagram, so that's the method I will use here. But any method is absolutely fine, as long as you show you're working right. So my cast diagram here then will look like the following. It's not perfect, but you get the idea. So what do we have here then? So in the bottom right corner, this is for cosine. Top right is all trigonometric functions. Top left then is for sine, and bottom left is for tan. Okay. Now this solution here then, x equals pi over 3, that would be here. Okay, so this solution then corresponds to this angle here. That's pi over 3 there. So given that we're working with cosine here, cos x, the next cosine solution then is in this quadrant here. Okay. So this angle here is also pi over 3. But what I want to know here then is what is the angle that's formed if we go from here, this line, essentially the x-axis, right, all the way around, until we meet this line here. Well, clearly one full turn here is 360 degrees, or 2 pi radians. So what we need to do here then is 2 pi minus pi over 3. So my next solution then, next solution is going to be 2 pi minus pi over 3. Obviously, you don't need to go into quite this much detail here, but I do want to make it clear what I'm doing. So 2 pi minus pi over 3, you can just use the calculator or get this over a common denominator then. So that would be 6 pi over 3 minus pi over 3 there, which would give us 5 pi over 3. Okay, so we get 5 pi over 3 there. So that gives us the next solution here. So 5 pi over 3. Now these two solutions here are what we call the principal solutions. Okay, and we do actually have one more solution here. And you need to be aware then that cosine is periodic every 360 degrees or 2 pi radians. So in other words, it just repeats every 360 degrees or 2 pi radians. So what that means then is my next solution now, so the next solution here would be this solution plus 2 pi. Okay, so next solution then. So next solution here is going to be 2 pi plus this angle here, so pi over 3. Okay, so in that case then, just get this over a common denominator here. And if we do that, we get 6 pi over 3 plus pi over 3, which gives us 7 pi over 3 there. Okay, so that then is my next solution, so 7 pi over 3. And at this point here now, we do have the full solution here, because if I take the next solution, then that would be 5 pi over 3, and add 2 pi to that, we fall outside of this domain here. Okay, so we would be greater than 3 pi. And obviously we can't accept that solution. So what that means then is this here is our full solution set here. Okay, so we'll just highlight that here then. So this is what you should get then for this question here. And hopefully this question wasn't too bad. Okay, so this is what you should obtain here then. That is our solution. Okay, and there we have it then. So that gives the solution there to question 2. So to finish with here then, we now have the very last question, question 3. So for this question then, as we can see here, right, we have this diagram. So this diagram here shows the sector OAB of a circle of radius 4 root 2 centimeters. We're then told that the area of the sector is 20 centimeters squared. So for the first part of this question here then, part A, all we want to do here is prove that the angle AOB is equal to 1.25 radians. So AOB then, that's this angle here. Okay, so we know the area of the sector here. And don't forget then to find the area of the sector here. Let's just write this down. So area of sector, this is equal to 1/2 times r squared times by theta. So r here then is just the radius, and theta would be this angle here. Well, we know then that the area of the sector is 20 centimeters squared. So we can set this here equal to 20. Okay. And in that case then, what we get here is a half times by the radius squared. So the radius here then is 4 root 2. So we've got 4 root 2 squared, like so. And then we times this by theta here. Okay. Like so. And this here then is equal to 20. Okay. So let's just simplify the left-hand side here then. So 4 root 2 squared. So 4 times 4 is 16. Times that by 2 because root 2 squared is 2. So 16 times by 2 is 32. Times that by half then, and we get 16 there. So 16 times theta here. So 16 theta is equal to 20. Okay. And then clearly here, if we just want theta, that's this angle here. We just divide both sides by 16, right? So nice and straightforward then. What that gives us here is theta is equal to 20 over 16. Okay. And 20 divided by 16 here just gives us 1.25. Okay. So we get 1.25 there. And given that this is this angle here, clearly it's measured in radians. So 1.25 radians there. So 1.25 radians as required. Okay. And there we have it then. So that gives us the solution to part A. So now for the second part of this question here, then part B, it says find in centimeters the perimeter of the sector OAB. So to find the perimeter then, let's do this in a different color here. Let's do it in light blue. The perimeter here is given as this length plus this length here plus my arc length here. Okay. So we know this length here. We know this length here. The other thing that we need to find then is the arc length, right? This arc length here, AB. So for part B then, let's do that underneath here. So the arc length here, AB. So for the arc length AB here, this is given as R theta. Okay, that's R here. That's this value here times by theta, which was given here in part A as 1.25. And obviously, we did derive that in part A anyway, but just in case you couldn't kind of derive it yourself, you do have it anyway. So you can still go on to answer part B and part C. So in that case, then the arc length here of AB, or the arc length AB, is R, which is 4 root 2, 4 root 2 times 1.25. And what that gives us here then is 5 root 2. Okay, get 5 root 2 there. So in that case then, the perimeter, so the perimeter here of the sector OAB, as we've just mentioned then, right? That's going to be OA plus OB plus this arc length AB. So let's just make a note of that as well here. So it's OA plus OB plus the arc length AB. Okay, so arc length AB. Okay. Clearly, you don't need to go into quite as much detail as I'm doing here. I do want to just show you all the steps of my working here as I go through the question. So OA then, that's 4 root 2. OB is also 4 root 2 here, as you can see from the diagram. So plus 4 root 2. And then finally, the arc length here, AB, as we've just evaluated then, that is 5 root 2. So plus 5 root 2 there, like so. And therefore then, if we simplify this here, what we get here then is 8 root 2 plus 5 root 2, giving us 13 root 2 there. We get 13 root 2 centimeters there. Okay. And there we have it then. So that gives us the solution to part B. And to finish with here then, let's have a go now at the very last part of this question, part C. So for part C then, we want to find to 3 decimal places the area of R. So R then is this shaded region here. So let's just make a note here then for part C. So for the area of R, then, well, that's given as the area of the sector OAB. So area of the sector OAB minus then the area of this triangle here, OAB, right? So minus the area of the triangle OAB. Okay. Now, we already know the area of the sector, right? That was given here. So the area of the sector is 20 centimeters squared. So that's fine. We've already got that to hand. So that's 20. So the only thing that we need to find here then is the area of this triangle here. And we can easily do that, right? So the area here then of this triangle, so area of the triangle OAB, we can find that by using a half AB sine C. Okay. So in that case, then what do we get here? So I get 20 minus a half. Well, A here would be 4 root 2, and the same is true for B. So B is also 4 root 2. I get 20 minus a half times by 4 root 2 squared. So 4 root 2 squared there. And then we times this by sine of this angle here. We've got sine of 1.25 there. Okay. So if we simplify this here then, what do we get? We've got 20. So 4 root 2 squared, as we know before, that was 32, times it by half then, and we get 16. So what I've got here then is 20 minus 16 sine of 1.25. Okay. So all you need to do here then is just put this into your calculator. Obviously, just ensure then that your calculator is in radians mode as opposed to degrees mode. And if you do this all correctly here then, what you should get then to 3 decimal places here is 4.816 there. Okay. And clearly the units here then would be centimeters squared. Okay. And there we have it then. So that gives us the solution to part C. This was the solution here to part B. And obviously part A was just to show that or prove that question anyway. So hopefully nothing too challenging there. And there we have it then. So that gives us the solution to the very last question here, question 3. And that brings us to the end then of this video here on exam revision for radians.